I had deleted, or I had gotten rid of the other graph, but if you can remember the graph, remember up here on the left-hand side, you had blue giants. Now, a lot of the material inside of a hot young star is inside of its monatomic configuration, meaning a lot of the material is completely ionized, meaning it's not attached to any molecular bonds or anything. It's a free-floating negative or positive ion or electron or whatever. And the only kind of energy it really can, or temperature it can have is caused by translational energy, meaning it moves through a material. It just can travel like this, okay? That's where the majority of the energy is comprised of when you have a monatomic gas or you have a completely ionized plasma. Now, the special thing is when that blue giant starts cooling and combining some elements into molecules, and it goes down in stages of evolution, and it becomes a much cooler red dwarf over many millions of years, because then it starts combining a lot of those elements into diatomic gases and other types of molecules. And what happens is, since the translational energy was only present there, now it can sustain a lot more thermal energy. It can hold a lot more thermal energy inside of it without having to radiate it away. Because what happens is the star creates molecules which then have vibrational energy, meaning these two parts go back and forth like this, and then you have rotational energy where the entire molecule can spin and can contain a lot of energy like that. Think about a dumbbell being thrown across a gym floor. Pretty dangerous. And you have translational energy as well, where the entire molecule travels from here to there. And over many more millions of years, these molecules start combining, making even larger molecules, and even more thermal energy can be held inside the molecule because you have the vibrational energy inside of all these bonds. The entire thing can spin. Think of a four-headed dumbbell being thrown across the gym. That's even scarier, like a giant dumbbell Chinese star type thing. And then you have that entire thing rotating, and then the translational energy on that would be a lot slower than a smaller molecule, but it would contain a lot more energy if it were to go. And this, when the molecule gets even bigger, now I use natural gas as an explanation because, well, natural gas is a byproduct of stellar evolution itself. It's not from decomposing plant and animal matter. That's 1950s propaganda for the oil industry. But as we all know, natural gas is a byproduct of stellar evolution through the theory of stellar metamorphosis. So here is another, I can't remember which molecule it says, I don't have them labeled, but it's a hydrocarbon chain. I think this is methane right here, I'm not too sure, I have to, and I think this is maybe propane, something like that, I can't remember. But if you have this molecule formed, it contains even more rotational energy when it goes from place to place, and even more translational energy, and even more vibrational energy between all these bonds. So you can add all those bonds together to hold more heat. And as we know, thermal energy, heat, is molecular motion. So you have vibrational molecular motion, rotational molecular motion, and translational molecular motion. And that is a very important part because as the star cools and dies, and it combines the elements into larger and larger molecules, these molecules also become heavier. So what they do, picture this as a star right here. This marker's dying on me. This is pathetic. Okay, so picture a star, okay? When it makes the molecules become heavier, and they drop towards the inner portions of the star. And the star will continue collapsing. So that's another mechanism for the collapse of the star, in addition to, I think, 8 or 9 other mechanisms, but you know, you get the point.